In the previous class, we introduced a new approach of transfer matrix method to analyze the torsional vibration, and today we will extend that particular method and we will try to illustrate the method's capability through some examples, so that the method application is more clear. And apart from that, we will see in the point matrix and the field matrix which we developed earlier, in which we did not consider the damping, torsional damping. So, what would be the change in the point matrix and field matrix if we include the damping also in the shaft system or in the disc system, we would see. And now let us see the overview of what we will be covering. So, damped torsional vibration, we will develop the transfer matrix for that. Even we will see torsional vibration in reciprocating engines. Some of the basic concept which we will cover is torsional damper, equivalent rotating system of reciprocating engines. So, these are the things we will try to cover in the present lecture. At the beginning, let us start with a simple example, so that the TMM method is more clear. So, for that purpose, I am taking a very simple example of a massless shaft, and at both ends there are two rigid discs and their polar moment of inertias are IP1 and IP2. This is mounted on frictionless bearing and it is free to oscillate on this bearing. So, as such, bearings are not resisting the motion of this particular rotor system. In this particular case, if we want to, earlier we have solved this using the Newton's law. Now, we will be using the transfer matrix method to obtain the natural frequency for such system. Let us say the stiffness of the shaft, which is torsional stiffness, is kT. Now, if we want to attach stations, so let us say this is 0 station and this is 1 station, because the rotor system is simple. So, we can have only 2 stations. Now, we can able to relate the state vector, or let us say we have state vector at 0 station, that means left of 0 disk, and we want to obtain state vector right of 0 station. So, we know that the state vector here is left of 0 disk and here will be right of 0 disk, and in between this there is a disk. So, we need to multiply this particular state vector with point matrix. We know the form of the point matrix, we already obtained earlier. Now, if you want to transfer the state vector right of 1, and we want this state vector from right of 0 station. So, for this purpose we already seen that we need to multiply by the transfer matrix for U1, and U1 we already seen is F1 into P1. So, you can able to see that this ordering is very important. How we obtain? Let us see again for clarity. So, basically we first need to obtain state vector left of 1 from state vector right of 0. So, state vector left of 1 is this one. So, if we want to transfer the information of state vector from here to here. There is a shaft, so corresponding we need to multiply by the field matrix. Now we can able to get the state vector right of station 1 as left of 1. So right of 1 is here. So you can able to see that in between the right of 1 and left of 1 there is a disk. So we need to multiply by point matrix, and if we substitute this here, we will get P1 F1 SL1, that is R0. This is subscript of the S. So you can see that the U matrix is having not this particular form. The ordering is important. P1 into F1. So this step is clarified through systematic approach, that U which we obtained earlier was having a form of this in which P into F1 was obtained. Now we can get the state vector. We can able to see that here we can able to substitute this. So we can able to get the state vector right of 0 as U1 into P0 S left of 0. So basically the first equation, this equation we substituted in the second equation here. So we got this particular thing. So you can able to see that this matrix, which is multiplication of 3 matrices, let us call this as overall transfer matrix, and the form of the T matrix is, that is U is P1 F1 and P0. This is the overall transfer matrix. Now let us see this state vector in expanded form which we obtained earlier. So we derived right of 1 as T matrix, and this is phi z T left of 0. So let us say these are, after multiplication of 3 matrices we get this T11, T12, T21 and T22. In the previous case, because both the ends of the disks are free, so torque at 0 station is 0. Also torque at 1 station right of 1 is 0, left of 1 is 0. So right of 1 is 0 and left of 0 is 0. So you can able to see that if we expand this, we will get from first equation, and this is from the second equation. And because this displacement cannot be 0 at free end, so we need to have from here T to 1, which is function of natural frequency, is equal to 0. So we have seen that how we can able to apply the boundary condition once we have obtained the overall transfer matrix, and how the frequency equation can be obtained. Now let us see in more detail after multiplication of various point matrix and field matrix, how this overall transfer matrix take the form. so that the things are more clear in the form of frequency equation, how we can able to get. So, now let us see the T matrix. T matrix we had as P naught, F1 and P1. So, if we this I am doing for illustration, but for larger system we need to program them so that we can able to easily obtain the roots of the frequency equation. So, this is the point matrix for 0 station. Field matrix is having this form for shaft 1. Then the field matrix or point matrix for disk 2 or disk 1 is, or station 1 is this one. Now we can able to multiply these. So, if we multiply these two, point matrix at 0 station and field matrix at station 1, we will get now I can able to attach the knots and the 1 here, because this is belonging to the 1, and here we will be having natural frequencies for the system. So, we will not attach any subscript for that, and the point matrix for this station 1. Now, if we multiply this, we will get IP1 by KT1, then 0 1 by KT1, and then minus omega NF IP naught and plus 1 minus omega square NF IP naught by KT1 and minus omega square NF IP1, and the last term is 1 minus omega square NF IP naught KT1. Basically, this we can able to shift here so that it is more clear, 1 by KT1. So, we have 2 by 2 matrix. This is the division of the matrix, separation of the matrix. Now, you can able to see that if we go back to the this T21 is the frequency equation that need to be equated to 0. So, you can see that this particular equation is the frequency equation. We need to equate this equal to 0. If we equate this equal to 0, we will get two roots. One will be 0 and another will be exactly same which we obtained earlier. This one here, basically I have replaced or I should have written 0 1 0 1. Earlier it was 1 and 2 in the analytical expression when we derive they were 1 and 2, but now because we are attaching the 0 and 1 station, but the form of the equation is exactly same as we obtained using the closed form solution. When the system is very large, then we'll be having difficulty in multiplying these matrices in analytical form or symbolic form. So in that particular case, generally we use numerical methods to solve the frequency equation. So let us see how it can be solved. So let us say the frequency equation, which will be function of omega nf, is this one. Now we cannot have explicit form of this particular component. So like for previous example, we had T21 of the overall transfer matrix, which is function of omega nf is equal to 0 we expect from to get the natural frequency. So let us say we are equating this particular component as a function of omega nf, and because the T matrix which we obtained, their multiplication of various point matrices and field matrices, and in all of them basically natural frequency is unknown. So unless we know this, numerically we cannot able to multiply the point matrix and field matrix. So for that purpose, when we solve the natural frequency using numerical technique, we assume some initial guess of the natural frequency, let us say very small value 0.01 radians per second. Once we assume this, then we can able to see whether this particular function, the frequency equation, whether it is satisfying this particular function, because this is the initial guess. So we don't expect that at the first initial guess this will be satisfied, there will be some residual, and obviously then we need to take increment in the natural frequency, assumed natural frequency. That increment can be further less depending upon the accuracy we need. So this will be the new natural frequency that is for the second step, and we'll again substitute this in the function and we'll see whether it reduces and increases, and in fact we can able to have a plot of the natural frequency chosen and this function, because now you can see that when we are assuming some natural frequency, this overall transfer matrix we can able to get in numerical form, because all the point matrix and field matrix will be known to us, and we need to see just this particular T21 component for the example which we have shown. For different boundary condition, different component we need to observe. So T21 for free condition we found as a frequency equation. So we can, once we plot this function, we may see that it may intersect the 0 line of the natural frequency. So that means this is one of the root of the natural frequency of the frequency equation, and depending upon the degree of freedom it may intersect at different places. So in general, if we have n degree of freedom, we expect n number of such intersection to get the n natural frequency of the system. This can be illustrated through this particular flow chart, that we assume some initial value of the natural frequency, estimate the frequency equation value, and we will see that this particular frequency value, because numerically it cannot be perfectly 0. So a very small quantity, if it reaches, if it is very small, then that is a solution. If not, then we need to again take another step of the natural frequency, and again we need to evaluate the this particular frequency equation. So, this cycle will repeat till we will get a desired accuracy of the natural frequency, and that will be the solution. And once we get one solution, we can search for more depending upon the degree of freedom of the system. So, we have seen that for larger system, what would be the procedure to solve the frequency equation. In this particular case, obviously numerical computation will be required to obtain the all the roots of the natural frequency. If there is some torque, external torque in the system, then the form of the point matrix and field matrix, we have seen that changes. Even the overall transfer matrix form will be changing. So, let us see how that particular form will take place when there is external torque in the system. So, you can be able to see that earlier we developed this overall transfer matrix, the transfer matrix between one shaft and the disc, and the form of the P matrix, modified point matrix and modified field matrix, where so this is the modified field matrix, this is the modified point matrix, and external torque was here. So, if we multiply them, it will be having this particular form. This is 3 by 3 matrix and the external torque is here. As such, this 2 by 2 first row and columns are same as the previous ones, only this is coming. So, now for a particular large system, if we have obtained the overall transfer matrix, so such transfer matrices will get multiplied, and if we multiply them, finally the form of the overall transfer matrix will be of this form, in which this will contain the external torque components. And now, because we have the external torque, will be having some frequency. So, those frequency will be appearing in each of these terms. So, you can be able to see that if we want the response of the system, because in this particular case we will be having the omega as the spin speed of the shaft, or the torsional external torque frequency, external torque frequency, this is the excitation frequency. So, if we want the response for various external torque frequency, we can able to vary this, and once we substitute in the various transfer matrices, they will be in the form of numbers, they can be multiplied to get the overall transfer matrix, that will also be in the form of number. So, we can able to get the response from this particular equation for various values of external torque. So, you can able to see that when this external torques will coincide with the one of the natural frequency of the system, we will be having a resonance condition. So, that also can be calculated using this particular equation, because this state vector contain not only the angular displacement, also the torque, and depending upon the boundary condition, we can able to get various displacements, angular displacements at various stations. Now, we will take some more example to illustrate the capability of the method for more complex boundary conditions. So, in that connection, let us take another problem in which there is a massless shaft and a disc is there at the end. This end of the shaft is fixed, and the free end of the shaft where disc is there, we have one torsional spring of the stiffness KT2, okay, and various dimensions of the shaft and the diameter of the shaft are given here. Even the modulus of rigidity is given to us of the shaft. We are neglecting the mass of the shaft, So for this particular case, first when we want to analyze using transfer matrix method, we need to assign stations. So let us say this is 0 station, disk location is station 1, and this fixed end of the spring is station 2. And once we have this, now we want to relate the state vectors at various stations in the left and right side of the disk, and try to relate the overall state vector relation. That means, let us say the state vector which is there at the station 2 and the state vector which is there at the station 0. So, and in between we will be having various field and point matrices. So, let us see this particular thing, how we will be having various state vectors. So, 0 station 1 and 2. So, here I am again repeating, there is a 0 station because there is no disk. So, we are not attaching any left and right to this state vector. Here we will be having state vector left of one station. Here we will be having state vector right of one station, and this is the state vector at station 2 because there is no disk here. So, it will be no left and right will be attached here. Now, you can able to see that between these two state vector there is a field matrix, and here between these two we have point matrix, and this spring is identical to a field matrix because this is acting just like a shaft with the same with the stiffness Kt is now Kt2. So, this can be considered as a shaft directly. So, now you can able to see that we need to relate all these state vector, and let us see the station 0 and right of disk 1 can be related by the multiplication of the field matrix and point matrix, and if we multiply this, this will be the expanded form of the transfer matrix. In this you can see the natural frequency expressions are there which is unknown, all other quantities are known. This is the state vector at 0 station, and this is the state vector at right of disk 1. Now, we want the state vector at station 2. So, for that we need to have multiplication of field matrix, point matrix, field matrix. This is corresponding to the spring. So, if we multiply this, we will get this 2 by 2 matrix, which is nothing but the overall transfer matrix for the present problem. But in this particular case, the boundary conditions are different. Now is fixed case. So, as we equated T to 1 equal to 0 for free case, this will not be the case. So, now let us see for fixed case what will be the. So, now we obtain the overall transfer matrix for this particular problem. Now, we will see, because now boundary condition is different, what will be the frequency equation. So, for that particular case, we have state vector at station 2 is equal to T11, T12, T21, T22 and state vector at 0 station. Now, as we can able to see, both the ends are fixed. So, that means here we have angular displacement 0 at station 0, and here also they are 0. So, these two boundary conditions we need to apply here. So, this is 0 and this is also 0. So, if we expand this to equation, we will get this from first equation. Second equation is So you can able to see that the first equation, because this torque cannot be 0 at fixed support, so we need to have this T21 equal to 0, which is function of natural frequency, like this. So this is the frequency equation. So you will go back to the previous case. So T12 is this one. So we need to equate this quantity equal to 0, that is the frequency equation. So you can able to see this is the frequency equation in which we are equating this, because this cannot be 0. So if we equate this term 0, we will get the natural frequency as this, and you can able to see this. This is the stiffness of the spring, this is the stiffness of the shaft. So as such, these two springs in the form of actual spring and in the form of shaft are basically connected in parallel. So that's why their stiffness are getting added directly, and this is the polar moment of inertia of the disc. Now for given values we can able to obtain the second moment of area, and this is already given. So all these quantities are known, so they can be obtained. The torsional, this is the spring of the torque is also given to us. So if we substitute this in the natural frequency expression, we will get this as the natural frequency in radians per second. So we have seen very simple examples, and in this particular case the aim was that how to apply the boundary condition, how to get the frequency equation. Now we will see a slightly more complex example in which we have two disks, and in this particular case the example is like this. So example is this one. We have a cantilever beam in which two disks are there, and various property of the disk, lengths, everything is given here, and we are considering the shaft as massless, only inertias are there at the disk, and this end is fixed and other end of the beam is free. So in this particular case, let us see if we have two disks. So this can be 0 station, is 1 station, 2 station. So you can able to see that we need to relate the state vector, which is here, right of 2 state vector right of, or because there is no disk, so at 0 station. And once we have related these two state vector, we can apply the boundary condition. Only thing will be here, the matrices will be more, will be multiplying more number of matrices. So let us see how this take place. So this is the overall transfer matrix. So is multiplication of P1 and F1 for the first shaft segment, and P2 and F2 for the second shaft segment. And in this particular case, you can able to see that if we want to get the state vector, let us say for right of 2, that means here, and right of 1. So for that we know this is the U matrix, which is multiplication of P and F, and similarly from the station 0, if we want the right of 1 state vector here, we need another transfer matrix corresponding to the 1, and this is U2. This is nothing but P2 into F2, and this is nothing but P1 into F1. So you can able to see that we could able to multiply these two and this here, and now we can able to multiply the, so basically this is nothing but, if you go back here, you can see this is u2 multiplied by u1. This is a 2 by 2 matrix, but they are having more terms. Now in the present case, the boundary condition is that the station 2 is free, so there will not be any torque, and station 0 is fixed, so the displacement will be 0 there. So this boundary condition we can able to apply here. So this is a different boundary condition as compared to the previous ones. So if we expand this in the form of, let us say, t, so the first equation will give us T12, that is torque naught. So T12 is this quantity, and the second equation will give us T22 T naught. So T22 is this one. So you can able to see that the second equation, because this cannot be 0 at free end or at the fixed end, so we need to have T22, which is function of natural frequency, should be equal to 0. So we need to equate this quantity equal to 0, which is function of natural frequency, and that will give us the natural frequency of the system. So the form of the expanded form of this T22, because that contains T21 also, is this one, and if we equate this equal to 0, we can able to get a polynomial. This is a quadratic polynomial basically in terms of omega n f square. This can be solved to get two natural frequency of the system. So basically you can able to see this is a closed form expression of that particular polynomial, and if we want to use various numerical values here, which is given in the problem, geometrical properties in stiffness and polar moment of inertia, we will get two natural frequency. This is the first one, 54.17 radians per second, and another is 187.15 radians per second. So we have seen that how to obtain the natural frequency using the transfer matrix method. Now once we obtain the natural frequency, the mode shapes can be obtained using the various transfer matrix equations which we related in between the stations. For that particular case, we need to obtain mode shape is nothing but the relative angular displacements at various disk location. So we need to obtain these relative displacements for each of the natural frequency which we obtained. So let us see how then the transfer matrix between various stations like 0 and 1 and 1 and 2, the intermediate transfer matrices, how they can be used to obtain the relative displacements between various stations. So for that particular case, if we see, this is the equation from the overall transfer matrix, but which we did not use. So if we go back and see, this particular equation we did not use, this was the frequency equation, and so this can be used to obtain this particular displacement. So if we, for a unit torque at 0 station, we can able to get a this particular angular displacement. So once we know this, that means we have state vector at station 2 known. This is 0 and this is T12, and T12 is function of natural frequency. So if we want to obtain the displacement for a particular frequency, we can substitute that frequency here to get that particular displacement. That means we know the all the field variable here. So once we know field variable at one station using various transfer matrices, we can able to get the field variable at any other intermediate location, and that is the thing we are doing here. So we can able to see that we are relating the field variable at station 1. So once we know this, we can able to get the field variable here, and even we can able to take the ratio of these two. So this is the ratio. So the ratio is in the form of this, in which natural frequency is one of the term. So you can able to see that if we substitute the values of the natural frequency, we can able to get the relative displacement between station 1 and 2. Station 0 is anyway fixed. So if let us see this for 2 natural frequency, what is the values it takes. So for first natural frequency, this is the value, and for second is negative. So you can able to see that we have mode shape corresponding to the first natural frequency. This is 0 station fixed, disk 1 location, this displacement, and here if we are taking unit displacement at station 2, the station 1 will be having 0.4349 unit displacement. Similarly here you can able to see that these two disks will be having anti-phase motion for the second mode. So in the first mode, both the disks will be having same phase motion, and in this particular case they will be having anti-phase motion. That means if this disk is rotating clockwise in torsional vibration, this will oscillate in the counterclockwise direction, and when the second is rotating in clockwise, this will be anti-clockwise for the second one case. So in the present lecture, we try to use transfer matrix method with various examples and various kind of boundary conditions, how we can able to get the natural frequency and how we can able to get the mode shape. We will be extending this particular method for the next lecture also for other cases like damped case and reciprocating engine case, which we could not able to cover in this particular lecture. And then once we have overall idea about this transfer matrix method, then we will go for the finite element method, which is more versatile, and the application of the boundary conditions are easier in that particular case.